That snowy TV screen isn't nothing. It's your living room picking up real signals you never invited, waves from your walls, your city, even the sky itself. And one of those sources is so old it makes your TV look young. So what are you actually watching? You've seen it, that dancing black and white snow on an old TV when there's no channel tuned in. It feels like the television is showing you nothing, but it's not nothing. It's the TV confessing something embarrassing. The room is full of electromagnetic waves all the time coming from everywhere, and when the set can't lock onto a clean broadcast signal, it has to display whatever random wiggles make it through its antenna and electronics. So the real question isn't why is the TV broken? The question is, what are those wiggles? Because once you admit the static is a real physical signal, just an ugly, unorganized one, then you can ask where it comes from. And that question has a terrifying answer. Some of it is older than the Earth, older than the Sun, older than the Milky Way. A small slice of that fuzz is literally leftover light from the early universe. Not metaphorically, not poetically, literally. Now don't jump too fast. If you've heard the claim TV static is the Big Bang, your brain probably does one of two things. Option A, that's a cool fact. You store it next to bananas are radioactive and move on. Option B, that sounds like internet nonsense. Because your TV is tuned to some VHF or UHF channel, tens to hundreds of megahertz, and the cosmic microwave background is called microwave. Microwaves are gigahertz. So how could a television possibly be seeing it? Good. That skepticism is healthy. Physics lives on that skepticism. Here's the more careful, more interesting version of the statement. When an analog TV shows snow, it's showing the combined effect of many noise sources. Some are inside the TV itself. Some are from your house. Some are from the atmosphere. Some are from our galaxy. And buried in that mess is a tiny contribution from a real measured glow of the universe, the cosmic background radiation, a nearly perfect thermal radio glow corresponding to about 2.7 Kelvin. It peaks in the microwave range, but it doesn't magically stop outside that band. Its spectrum has a long tail down into the radio frequencies where TVs listen. The TV isn't tuned to 160 gigahertz. It's just sensitive to random electromagnetic power in its channel bandwidth, and the universe provides a little bit of that power everywhere. So the statement isn't that the whole snowstorm is the Big Bang, it's that the Big Bang is part of the snowstorm, and that's actually a deeper idea than it sounds, because it means cosmic history isn't out there. It's not only something you point a billion-dollar telescope at, it leaks into your living room as a faint hiss. Let's pin down what we're even looking at. An analog television takes a voltage that wiggles in time and paints it as brightness on a screen. When a TV station broadcasts a picture, that wiggle has structure. The wiggle is organized so that when you sweep it line by line, you get a face, a football game, a weather map. When there's no station or the station is too weak, the TV still has to draw something. The amplifier in the front end is still amplifying. The antenna is still an antenna. The circuits still have electrons jiggling in them, so the input becomes dominated by random fluctuations. The TV paints those as random black and white dots. So snow is the visual form of randomness in the incoming electromagnetic signal. Now, where does randomness come from in physics? From heat, from motion of charges you're not controlling, from the fact that atoms are not politely sitting still. A warm resistor is not quiet. The electrons inside it have thermal energy, and they rattle. That rattling produces a tiny random voltage called thermal noise. Every real amplifier adds noise. Every cable picks up noise. Every antenna collects noise. So even if you unplug the antenna entirely, some televisions will still show a kind of snow, because the noise is being generated inside the set. That's one big chunk. The machine making its own chaos. But connect an antenna, and now the TV becomes a bucket for electromagnetic junk from the environment. Your home is full of it. Light switches spark a little, motors make interference, computers radiate, power lines hum. There are radio stations, cell towers, Wi-Fi, all screaming. Lightning strikes on the other side of the planet, and the radio crackle can travel. The Earth itself is a noisy ball, and above all that, space isn't quiet either. The Milky Way emits radio waves, not because the galaxy is broadcasting music, but because charged particles spiral in magnetic fields and radiate. Interstellar gas glows at specific radio frequencies. The sun spits out radio noise. Even distant galaxies contribute a background. The sky has a radio temperature. If you could translate radio noise into how warm does this look, some directions in the sky look hotter than others. So already you can see the problem. that TV snow is a cocktail. If I show you a glass with 10 different clear liquids mixed together and I say, a drop of this came from an ancient river, you'd ask, how do you know? How could you possibly separate that drop from everything else? Exactly, that's the real problem. Because the cosmic microwave background, this afterglow of the early universe, is not some special magical kind of light with a label on it. It's just electromagnetic radiation, photons, same kind of thing as radio waves, microwaves, infrared, visible light. It obeys the same rules as every other wave your antenna can pick up. So if we're going to claim any fraction of TV static is the CMB, we need a way to justify it, not with vibes, with physics. And the physics starts with a simple but unsettling point. Empty space is not empty of signals. It's full of energy in the form of fields, and those fields can be in random thermal states. If you have a bath of radiation with some temperature, then any receiver connected to an antenna will see a corresponding noise power. That's not philosophy, that's engineering. It's literally how radio astronomers and communication engineers design receivers. They talk about noise temperature as if the sky is a warm object, because for a radio antenna it is. So the universe itself looks like a faint warm glow. And here's the strange part. That glow has a temperature you can measure, about 2.725 Kelvin, almost 3 degrees above absolute zero. It's astonishingly uniform across the sky, with tiny variations at the level of 1 part in 100,000. And those tiny variations are not random junk. They're the imprints of early density ripples that later became galaxies. That's why people call it the baby picture of the universe. Not because it's cute, because it's a snapshot of the universe when it was hot enough to be opaque, and then suddenly became transparent, letting radiation travel freely for the first time. If you accept that, then the TV snow becomes a creepy thought. Some of the randomness hitting your antenna is a fossil from the moment the universe first became see-through. But we're not allowed to just accept it, we have to earn it. So the problem we're going to define carefully is this.
Want to deal with is static, physically, in terms of fields, power, and randomness. 2, what are the dominant noise sources in an analog TV and why do they look random? 3, given all those noise sources, is it even meaningful to say a % of the static is cosmic background? 4, and if it is meaningful, what exactly does left over from the Big Bang mean in a way that doesn't turn into mystical nonsense? Because if we do this right, the payoff isn't a trivia fact, the payoff is a shift in how near the universe feels. You don't need to travel anywhere to be bathed in cosmic history. You're already inside it. Even now, as you sit there, photons that have been flying since long before the first star are passing through your body. Most go through without interacting. A few get absorbed as heat. They are as ordinary as warmth. But their origin story is insane. And there's a catch, there's always a catch. Your TV is not a precision cosmology instrument. It's sloppy. It's designed to show sitcoms, not map the early universe. So the CMB contribution is small, and it's mixed with everything else. If you live in a city, man-made radio noise can swamp the sky. If your antenna is indoors, it picks up local junk. Even the TV's own electronics can dominate. So if what you want is the clean baby picture, you don't use a television. You use a radiometer on a satellite with careful calibration, sweeping the whole sky, subtracting foregrounds, correcting for the motion of the Earth, the motion of the Sun, the motion of the galaxy. But that's exactly what makes the TV fact so beautiful. Even a crude receiver can't completely escape the universe. The universe leaks in. So before we talk about the Big Bang, before we talk about leftover light, we have to get comfortable with a more basic idea that most people never truly digest. Noise is not the absence of a signal. Noise is a signal you don't understand yet. And the moment you take that seriously, TV snow stops being annoying. It becomes a clue. So let's turn the clue into something you can actually calculate. Take a TV antenna. It's just a piece of metal that's willing to let electromagnetic waves shove charges back and forth. If a wave arrives, the electric field makes electrons in the metal jiggle. That jiggle becomes a tiny voltage. The TV amplifies it, demodulates it, and tries to interpret it as a picture. When the incoming voltage is random, the picture is random. Now here's the key engineering idea. Any random electromagnetic field can be described as if it came from something warm. Not warm like touch it and it burns. Warm like it has thermal radiation. If you put an antenna inside a closed box whose walls are at some temperature, the antenna will see a random radio signal, and the average power of that signal depends on the temperature. Hotter walls, stronger noise. Colder walls, weaker noise. This is not philosophy, it's a measured fact called thermal radiation, and for radio frequencies it turns into a very simple rule.
At low frequencies, where low means the photon energy is much smaller than the typical thermal energy, each little slice of bandwidth carries about the same amount of power proportional to temperature. In other words, if the sky looks like a 3 Kelvin object to your antenna, then in a given bandwidth it injects a predictable amount of noise power into your receiver. It's like the universe is whispering, and the loudness of the whisper has a thermometer reading. That's why radio astronomers talk about the brightness temperature of the sky. They literally ask, if this radiation were coming from a black body, what temperature would it have to be to produce this intensity? Now, the cosmic microwave background is special because it is extremely close to a perfect black body spectrum. One temperature, about 2.7 K, almost the same intensity in every direction, after you subtract our own motion.
So if your antenna points at empty sky, there is a baseline radio glow that corresponds to roughly 2.7 K plus other stuff piled on top. Our galaxy, the atmosphere, the ground, your house, your electronics. And now we can say something precise. Even if you could eliminate everything local and everything galactic, you still cannot make the sky colder than 2.7 K. Not in the microwave and radio bands where the CMB lives. There is a floor. That floor is the afterglow. But wait, your TV is not a lab instrument, and it's not sitting in empty sky. It's in a room. So why would it see any of this cosmic floor at all? Because an antenna doesn't only see what's in front of it like a camera. It has a pattern. It sees some of the sky, some of the walls, some of the floor, depending on its design and where it's placed. And whatever it sees, it averages into noise power. If the antenna sees your warm walls, it also sees a black body at about 290 K. That is 100 times hotter than 2.7 K. So in a clean room with a perfect antenna pointed at your house, the dominant thermal radiation is from the room, not the cosmos. So how on earth could the cosmos be visible? Two reasons. First, the room's thermal radiation at TV frequencies doesn't couple efficiently into a typical TV antenna the same way it would at infrared, because the wavelengths are long meters. Your walls are not a perfect radio blackbody in the way they are at heat wavelengths. The room is complicated. Reflections, impedance mismatches, the antenna pattern, polarization, and the fact that the TV is not measuring absolute temperature, it's measuring fluctuations after amplification. Second, and this is the practical one, most of what you call static is not the absolute power level, it's the randomness after the TV has cranked up the gain trying to find a station. A tiny change in the incoming noise can become a visible change on the screen. So yes, the CMB is small, but small doesn't mean zero. And TVs are absurdly sensitive to tiny voltages because they have to pull broadcasts out of the air. Now let's tackle the big objection. The CMB is microwave, my TV is VHF UHF. The phrase microwave background names where the spectrum peaks, not where it exists. A blackbody spectrum is not a razor blade that cuts off. It's a curve. It rises, it peaks, it falls, and it has tails. The 2.7 K blackbody peaks around 160 gigahertz, definitely microwave. But it still produces radiation at 1 gigahertz, 100 megahertz, 50 megahertz, just less of it. So can that tail contribute to TV snow? Yes, in principle. But you want to know how much? Not in principle. Here's where we have to be honest. If you take a typical analog TV, a typical indoor antenna, and a typical environment, the CMB is not the dominant cause of the snow. It's a fraction of a fraction. A lot of the snow is the TV itself. Thermal noise in the tuner, shot noise in the electronics, amplifier noise. Engineers quantify this with a noise figure. Real amplifiers add their own effective temperature, often tens to hundreds of Kelvin equivalent. That can swamp the 2.7 K background by a lot. Then there's man-made interference. Then there's the galaxy. Then there's reflections. Then there's atmospheric noise. Then there's the fact that the TV channel bandwidth is several megahertz, which sets how much noise power gets integrated. So if you want a single clean number like exactly 1% of the static is Big Bang, that number depends on the TV, the antenna, the channel, the location, and the era. The famous popular science line often quoted is about 1%, sometimes a few percent, but you should treat it as an order of magnitude story, not a universal constant. The correct physics claim is more subtle, but more satisfying. There exists an irreducible isotropic radio background with a blackbody spectrum at 2.7 K. Any sufficiently sensitive radio receiver in a sufficiently quiet environment will detect it as part of its noise. An analog TV receiver is a radio receiver. Therefore, the CMB can contribute to its static. That's the real statement. Now, if you're still annoyed, okay, but what does it mean that it's left over from the Big Bang? Good, because that phrase is dangerously easy to misunderstand. Most people imagine an explosion. A point in space blows up, throws debris outward, and the debris is still flying through space. That picture is wrong. The Big Bang in modern cosmology is not an explosion in space. It's the early state of the universe where everything was hot and dense everywhere. Space itself was filled with plasma, electrons, protons, photons, so tightly coupled that light couldn't travel freely. Photons were constantly scattered by free electrons. If you were inside that early universe, you couldn't see far. The universe was fog. Then the universe expanded. Expansion doesn't just mean things move away. It means the scale of space grows, so wavelengths stretch, and as it expanded, it cooled. Eventually it cooled enough around 3000 Kelvin that electrons and protons could combine into neutral hydrogen without being immediately ripped apart by energetic photons. When that happened, the number of free electrons dropped dramatically. The fog lifted. Photons stopped bouncing every millimeter and started traveling long distances. That moment is called recombination, and the surface we see is called the last scattering surface, because those photons were last scattered then, and after that they flew mostly straight. Those photons are the cosmic microwave background. They were once the color of visible and infrared light at 3000 K. Not microwave, but the universe stretched their wavelengths by about a factor of 1100. So what was once a warm orange glow is now a cold microwave bath. So when you say leftover from the Big Bang, what you really mean is photons that decoupled from matter when the universe became transparent and have been free streaming ever since, redshifted by cosmic expansion. It's not debris, it's not smoke, it's not a shock wave. It's just ancient light, cooled by geometry. And the reason it's everywhere, this is the part that makes people's brains click, is because the early universe was everywhere. There isn't a single direction you can point where you avoid it. Every line of sight eventually ends on that last scattering surface, like looking outward from inside a foggy sphere where the fog boundary is set by time, not distance in the ordinary sense. So your living room is not far away from it. Your living room is inside the same space-time. The CMB photons are passing through your living room right now. That's the unsettling bridge between cosmology and your TV. The television is not looking across a gigantic distance in the way a telescope does. It's just picking up local electromagnetic fields that happen to include a cosmic component. The cosmic part is faint, yes, but conceptually it's enormous, because it tells you the universe carries its own memory as radiation, and that memory is not locked in a museum. It's leaking through the air. So what do you do with that idea besides repeating it at a party? You test it, at least in spirit, because the whole point of physics is that it feels true is worthless. You want handles. You want ways the universe can say yes or no. Here's one handle: direction. If you could take a simple radio receiver and point it at different parts of the sky, you wouldn't see pure uniform noise. You'd see the Milky Way. You'd see the galactic plane hotter in radio. You'd see the sun as a bright radio source. You'd see storms on Earth adding crackle. You'd see your neighbor's electronics if you get close enough.
And buried under all that, if you average long enough and subtract carefully enough, there's a background that doesn't care where you point. It's almost perfectly the same everywhere. That isotropic part is the cosmic background. Your TV, sitting in a room, is terrible at this game. It's not scanning, it's not calibrated, it's not measuring absolute power, it's not even designed to tell the difference between sky noise and its own internal hiss. But you can still grasp the logic. If there is a universal background radiation, then no receiver is ever truly listening to silence. The best you can do is listen to the universe's baseline. And here's another handle: spectrum. Man-made noise often has fingerprints, narrowband carriers, harmonics, patterns. Galactic synchrotron radiation has a different frequency dependence than a blackbody. The atmosphere has features. The ground has features. The CMB, on the other hand, follows a blackbody curve so cleanly that it's almost insulting. It is one of the strongest pieces of evidence we have that the universe really did go through a hot, dense phase. That matters. Because cosmology is full of things you can't repeat in a lab. You don't get to run the universe twice and compare. So you cling to the things nature gives you that are clean and unmistakable. The CMB is one of those. So when someone says TV static is the Big Bang, the grown-up response isn't to sneer or to clap. The grown-up response is, yes, there is a real cosmic radiation field left over from early times. Yes, a crude receiver can pick up a small part of it. No, your entire screen is not a direct map of the early universe. And yes, the fact that it leaks into ordinary life is philosophically violent, because it changes what far away means. We have this instinct that the past is distant, like a city you can't reach.
The Big Bang sits at the end of some corridor labeled billions of years, and you imagine it locked behind glass. But the universe doesn't work like that. Time is not a place you travel to. The past leaves artifacts, it leaves fossils, it leaves photons, and those artifacts continue to exist now in the present as real physical stuff. The CMB photons are not images of the past in some abstract way. They are particles of light, real energy and momentum, moving through your room. They could in principle be absorbed by your skin and become an extra microscopic jiggle in your molecules. They could warm you by an absurdly tiny amount. They are physical visitors, and there's something else hiding in that statement that people miss. If you accept that the universe has a background radiation at 2.7 K, then space itself has a temperature, not because space is made of gas, but because space is filled with a radiation field that acts like a thermal bath. If you put an object in deep intergalactic space and isolate it from everything else, it will not cool to absolute zero. It will radiate energy away until it equilibrates with that bath. It will settle near 2.7 K. So the universe is not a cold, empty void with occasional hot stars. It's a warm ocean of ancient light with hot sparks floating in it. That's what your TV static is hinting at. Now zoom out one more step, because this is where the whole story becomes personal. When you look up at the night sky, you see stars. You see points. You see objects. You can trick yourself into thinking the universe is mostly things with emptiness between them. The CMB is the opposite. It's not an object, it's a condition of the whole sky. It's a background you can't point away from. And those tiny temperature ripples, 1 part in 100,000, are not decoration. They are the seeds of structure. They are the reason there are galaxies instead of a featureless fog. They are the reason matter clumped into stars. Stars forged heavy elements. Planets formed. Chemistry happened, and eventually you happened.
So, if the CMB is a baby picture, it's not just the baby picture of the universe. It's your baby picture too, in the only honest sense physics allows. It's a snapshot of the conditions that made your existence possible. And that's why it's so satisfying that it shows up as random noise, because that's how the universe always behaves. The deepest truths don't announce themselves with trumpets. They show up as a small offset, a faint hiss, a stubborn residual you can't get rid of. Some engineer tries to build a quiet receiver and keeps seeing a tiny background. They check the amplifier, they check the antenna, they check the ground, they check the pigeons in the dish, and the hiss stays. That's not just a technical detail. That's the scientific method in its purest form. You keep subtracting your own mistakes until nature is the only thing left making noise. Now there's a tempting mistake to make here. People love to take a statement like this and turn it into mystical comfort. See? The universe is right here with me, I'm connected. Careful. Physics doesn't give comfort, it gives clarity. The connection is real, but it's indifferent. The CMB is not aimed at you, it doesn't care about you. It's just there because the universe expanded and cooled and became transparent, and light kept going. And that indifference is exactly what makes it beautiful. No one arranged this to be poetic. It just happens to be true. So here's the closing thought I want to leave you with. Your TV static is not a message. It's a reminder that the universe has a past that still physically exists. The ancient light is still here. The early heat is still here, diluted, stretched thin, almost whispering, and you are living inside that whisper. If you want to keep going, if you want the next step past the trivia fact, we can do it the right way. What that 2.7 Kelvin really means, why the spectrum is such strong evidence, how we know it's not dust or stars, and how those tiny ripples turn into the entire cosmic story of structure. Because the most honest summary is this: the cosmos isn't far, it's not even outside, it's in the noise floor of your life. If you want physics that keeps doing that, taking something ordinary and showing you the ancient machinery behind it, stick around.